valence shell electron-pair repulsion theory and valence bond theory for borate. And this is an example of exception to the octet rule. You start off by reading the chemical formula for borate. Borate is composed of 1 boron atom, 3 oxygen atoms, and this is a polyatomic anion with a negative charge of 3, so it has an excess electron of 3. This is the orbital notation for boron. As you can see, the 2s orbital is paired and there is a half-filled 2p orbital. For oxygen, the valence electron is 6 and 2 orbitals are paired. There are 2 half-filled orbitals, so in order to attain octet rule, having 8 electrons in the outer energy level, it will need to get 2 electrons shared with it. Right, so next step is to determine, so since this is bonded together to form a whole unit of polyatomic ion, the next step is to determine which of these is the central element. So with that, the basis is the electronegativity of this element. So the one with the lower electronegativity is usually chosen as the central atom. So here, boron has an electronegativity of 2, oxygen 3.5. So we'll choose boron as the central atom. Oxygen with the higher electronegativity will as much as possible take oxygen to whom it is bonded with. So it's not a good central atom compared to boron, which readily gives its electron to the atoms where it is bonded with. Right, so let's form a list here. The central element again is boron. So let's propose a Lewis dot structure with boron at the center. Alright, so oxygen at the side. And let's not forget, borate is an ion with an excess electron of 3. So we'll distribute this excess electrons to the electronegative element oxygen because it takes, okay, so it is electronegative, it takes electrons with it. So let's place one here, then another one here. Right, so let's rearrange this. So we didn't take anything. We just rearrange it in terms of drawing in order to, let's say, try to bond it with our central atom, which is boron. So excuse me for saying element and atom interchangeably. Right. So here we also rearrange it for our central atom, boron. Okay. So remember that in one bond, single bond, there are 2 electrons involved. So we can form single bond with each of this oxygen to the central atom, boron. So as you can see here, oxygen will obey the octet rule. Oxygen, okay? So when we say exception to the octet rule, we pertain to the central atom. Okay, so the atom at the side bonded to the central atom will obey the octet rule, especially oxygen. But for our central atom, boron, it won't. Okay, so here you can see, again, we rearrange it. So oxygen, this one has 8 electrons bonded with it, and one of its electron shared with boron here. So this is single bond, 2 electrons are involved in single bond. This one is bonded with the electron of boron, and also this one. So 8 electrons for each of this oxygen. For boron, as you can see, how many electrons are shared with boron? 1, 2, 3, 4, 5, 6. So it has only 6 electrons. It doesn't obey the octet rule. But we can, I'll show you a model later on that we can force the octet rule on boron, but we will also prove why it is wrong to do that. To show you how, let's say, these 2 electrons, okay, so we can move it here. So we can move these 2 electrons here and bond it with boron. So in effect, this oxygen will have like 8 electrons still shared with it, and now boron will have 8. Okay, so that is also possible in theory, but I'll show you by using formal charge that it's not good to, it's not stable for that form to happen. Right, so the Lewis dot structure is this one, and it's drawn here. So let's just place it here. Hope you can still see it. So we place a bracket here. If it's a polyatomic ion or an ion, usually place a bracket here, and there's a superscript here what is the charge of the species. Right, so again, 2 electrons are involved in a single bond. Formal charges of each. So the computation for formal charge is equal to group number minus the summation of number of bonds plus the number of unshared electrons. Another way to express this in a much, in a way that you can memorize it better is group number is equal to the summation of lines plus dots. So for this computation is done for each of the atoms involved in the unit, in the species. Okay, so for boron, using this Lewis dot structure, so if this Lewis dot structure is final, we can use formal charge, or if we can also use formal charge to do trial and error. Alright, so for the formal charge for boron is, you can see the central, it is our central atom. Boron is group 3 in the periodic table, and this boron has 3 lines, or 3 number of bonds, and no unshared electrons, so no dots. So we get here a formal charge of 0. For our oxygen, so all of this oxygen looks the same. So oxygen is, so we'll use the same computation. Oxygen is a group 6 element. 1 line associated with it, and 6 elements. 6 electrons, 6 dots. Okay, so the formal charge for each of this oxygen is -1. So the formal charge is distributed. Okay, distributed in this unit, so it's -1 for each. So for a total of -3. So the total formal charge should be equal to the charge of an ion. Now let's try the model that I showed you earlier. What if we force the octet rule for our central element? So what if we force this so that boron will obey the octet rule? Okay, so this is possible in theory, but let's see. Let's use formal charge computation. Boron here will have as you can see, boron group 3 element, 4 lines attached to it, so or 4 number of bonds and 0 unshared electrons. There is a double bonded oxygen, so ODB, double bonded oxygen. Group 6, 2 lines, 4 dots, 0 formal charge. Single bonded oxygen, 6 -1, 6 negative. So it's the same as the computation here. Single bonded, I hope you already can see that. So the formal charge is still -3, right? So we still get this, but as much as possible, if you have here an electronegative element, oxygen, and a lesser electronegative element, boron, the most stable configuration is one in which the more electronegative element will have the negative charge, right? So here, boron has a charge of -1, and oxygen, more electronegative element, 0. This is not as stable as compared to this one, so we'll use this. So by using that formal charge computation, this model is better compared to this model, right? So we'll use this model to move on to the next step, and that is determining the geometry of this polyatomic anion. So next, let's get the electron group or steric number for the central atom. So steric number, single bond, double bond, or lone pair associated with the central atom is considered as 1 count. Here we have 3 single bonds, no double bond, no lone pairs. So we still have a steric number count of 3, or electron group count of 3. So there's 3 electron groups associated with our central atom, boron. So you can see this table in chemistry books. This is molecular geometry, electronic geometry. This is about valence shell electron pair repulsion theory. So for molecules, polyatomic ions with 3 electron groups, the possible geometry, electronic geometry, is trigonal planar. And trigonal planar can have 2 molecular geometry. So when you say molecular geometry, okay, so electronic geometry is about the electron groups. So it could be double bond here, single bond, or lone pair. molecular geometry, this is actual atoms bonded to the central atom. So if those electron groups, these 3 electron groups are associated with actual atoms here, you'll have a trigonal planar molecular geometry. Same with the electronic geometry. But if that is a lone pair here, L stands for lone pair, you'll have an angular molecular geometry. So for this one, we have 3 electron groups, and those electron groups are associated with an atom bonded to a single bond to the atoms. So our electronic geometry and molecular geometry are both trigonal planar. So the electronic geometry is trigonal planar. The molecular geometry is also trigonal planar. So this talks about the arrangement in space of the atoms that forms borate. Trigonal planar is said to be sp2 hybridized. What is the meaning of sp2 hybridized orbital? First, let's check the orbital notation for our central atom, boron. So boron has an orbital notation of 1s2, 2s2, 2p1. And sp2 hybridized means that the one that will be involved in bonding is 1s orbital and 2p orbital. So in order to accommodate bonding with these oxygens, our central element will have to form this hybridized orbital in order to accommodate bonding. So it will look like this. This electron here, this field orbital here, its electron will have to jump to this one, to the other p orbital, in order for this remaining, so it will form these 3 half-filled orbitals. So in order for it to be filled, right? So in order for it to be filled, the electrons here, these electrons will be filled by the electrons from the oxygen. Okay, so sp2 hybridized means that our central element will use 1s orbital and 2p orbitals. Okay, so sp2, and this half-filled orbitals will form single bond or sigma bonds with these 3 oxygens. So there you go. I hope you learned something in this video, how to solve VSEPR and valence bond theory hybridization problems. I'll show more for this kind of problems. Alright, so thank you for watching. I hope you learned something. Goodbye.